Yeah, it's supposed to be a school, so we just start as a lecture, no introductions. But I'm Sanjeev Arora, pleased to see you all. This is the first of the 3 lectures, and it's sort of a survey. It'll introduce some of the themes of the other 2 lectures. And we all remember a couple of years ago when language models suddenly were released and became very popular. And there was this controversy that they are parrots. And there was this controversy, and for some people it still exists, that this method, which is basically next word prediction, that you're given, the model is given a sentence and it learns to compute the distribution on the next word. And it was just inconceivable to people, and for many people still is, that this autocomplete, glorified autocomplete, can lead to intelligence. And there was a famous paper, maybe now infamous, which claimed these are the stochastic parrots. And indeed, I mean, for any reasonable person, like, this is not how humans learn, right? That you just train by gradient descent to get better at producing this distribution. And maybe language is not even a distribution, because we can reason and then decide to say arbitrary things. It feels like, right? It's not a distribution. In linguistics, Chomsky, the god of linguistics, for many decades had championed this idea that there's something special about language, and humans actually have this language organ, he called it. I mean, nobody's ever found that organ, but like conceptually, we're saying there's something biologically special about humans that leads to language. These days, people don't believe that as much, and he himself has he changes his mind a little bit too. But still, just last year, there was this article in the New York Times, ironically by a science fiction writer, famous science fiction writer, why AI isn't going to make art. And I just kind of pasted that paragraph. I mean, even when I read it, I said, oh, this is perfectly used in lectures about like what people, what non-experts think about, what non-experts see when they see network vision. So he's talking about why it cannot be original, and if you are asked to write a 10,000 word story, there are various ways you can do it. It can take an average of the choices, or it can emulate one specific writer, mimic one specific writer. These are the 2 choices he can conceive of. Just a show of hands. How convincing is that argument to you? That it cannot create something new, because these are the 2 things it can do. It can either take the average of the choices of all other writers, or it can mimic one specific writer. How many of you find that plausible and convincing? Nobody? How many things is, oh, 1 or 2. And the rest, do you think this is nonsense, or could be right? How many people think it's nonsense? No, this person's argument.
I would say when a model fully overfits, it agrees with these, either takes an average or takes a special.
No, this writer is not talking about, he doesn't know about overfitting, I presume. So he's talking about models that he's interacted with, which you have to try.
In general, if you knew about anything about how these work, then this discussion will make sense. Because in general, it's an average thing, and it can make nonsense when you have the average of different writers and the stuff.
Is it the average?
So I think that talking about a simple average is like underestimating some of the capabilities, no? this model. And also, so the idea is that there are these models which are in some ways semantic models, so they can understand to some extent the meaning of what they are looking at as an input. No? So we're talking about a simple average of the choice they have been trained on. I think it's like underestimating some of the actual capabilities of these models.
Yeah, great. Yeah, so you bring up an excellent point, which is exactly the theme of the lecture, understanding. Are these things understanding? Indeed. And as you say, if they are understanding, then they can do many more things. Yeah. So that's indeed the rest of the lecture. Next word prediction is more powerful than it looks. And we'll see that models have some awareness, and we'll see what that means, of their own thinking and their own skills. What's called metacognition. The other thing I'll briefly emphasize is that this view of language models being you just train them with next word prediction on a bunch of internet text, that's very outdated. And that's actually the source of many of the improvements in the last 2-3 years. Then I'll briefly survey some of the advanced ideas that are going on in language models these days, beyond just take a bunch of internet text and do train on next word prediction. And we'll talk about these science fiction ideas, scaling laws, just briefly. Scaling laws, models are training models. There's self-improvement in the model. The model is in effect training itself and agents. And then we briefly discuss also along the way issues arising in the future, like ACDL and stuff like that. And lectures 2 and 3 will build upon this. Any questions, comments? Okay, so to make sense of this whole field of AI today, you have to start with a better lesson. This certain pioneer, he wrote this article in 6 years ago. It says this, this is the key line, the biggest lesson is, and he's been around for decades himself, I think 5 decades, and is that general methods that leverage computation are ultimately the most effective. So we'll return to this, how these notions arose from are actually a very good example of the better lesson. Okay, so the next word prediction is actually more powerful than it seems. By the way, the next word prediction, the idea has been around since the 1950s. How many knew that? Wow, only a few. Yeah, so Claude Shannon, who was a pioneer in information theory, was already talking about these models, next word prediction. But basically, those were n-round models. But the idea was the same, that you're trying to predict the next word, given the past few words. And then the modern wave started around 2013 when deep learning took off. And then there was this paper which introduced the transformer model, attention is all you need, which is, I think, the most cited paper in all of science in the last 10 years. Okay, and next word prediction, we've already seen this. Formally, it's a model that, given the previous I words, will give a distribution on all possible words, meaning all dictionary words. And technically these days, the basic unit of text is not word but token, but for this talk we will ignore that difference. And the training objective is to minimize cross entropy, which is defined as follows. For a word sequence W1 to Wn, it's the average of this, the log of 1 over the probability of the next word given the previous I words. So this is what the model is computing, this probability, and the objective is to minimize this. Now if you stare at it, it indeed looks like it's, what you would want to do is give, in the actual text that you're given, the corpus, you would just try to give the largest possible probability to the word that actually occurs. But turns out that in practice, the training set is very vast, much larger than the number of parameters, and so that overfitting does not happen. Okay, and we'll revisit this in the second lecture, what the meaning of this clause is. But for now, but for this lecture, let's just note that this probability will capture variation of style, lingo, topics, etc. Because the completion, depends on all of those things. And the other reason why next word prediction is a nice thing, a nice way to train a model, is that it also naturally leads to text production. Because to produce text, you just produce the next word. Now you take that word and loop it back and put it into the input and produce the next word, etc. And so you get pages or books of text, whatever you like. And this randomness is a source of diversity, but it's also a source of hallucinations. Okay, so why train LLMs on next word prediction? When there are all kinds of famous people say, come on, this is a stupid idea. Why is it still so popular? Well, you require massive training sets, like 20 trillion words these days, which is something like 10 pages of text for every human on Earth. And next word prediction gives a way to turn it into a prediction task, right? The text is there, and you're just training the model on that text to predict the next words. And that's a form of self-supervised learning. And now this is the important part, and why this is very compatible with the bidder lesson. The effectiveness, so firstly you have a lot of text, right? So that's one part of bidder lesson, right? It should be able to scale up. And the second is, this actually is not mentioned in the bidder lesson, but is an important part. That the effectiveness of next word prediction training does not plateau even at very large scale. People kept scaling it up, and it still yields improvements. In contrast to, some of you may remember, like 7-8 years ago, there was this bird skull transformers. Those plateaued. So, that's why. And then finally, it has some shortcomings, but they can be patched by other stages of training, as we'll see. Okay, so next thing I want to talk about is the idea of skills in language models. And by the way, I'm talking primarily about language models, but these days, the other AI models, or many of them, are very similar to language models, and the discussion generalizes to those. Okay, so skills, nobody has ever defined precisely what a skill is, like mathematically. But let's just think of it as a way to do something, or a procedure. And procedures can be chained together in novel ways. So this can be an important source of originality, as was mentioned by somebody. So next word prediction requires learning procedures. It's not just about memorizing training text. And let's see why. Suppose the term metaphor didn't exist. Okay. How many people don't know what a metaphor is? Okay. So suppose the term metaphor didn't exist. You'd still have an intuitive concept of metaphors and how to create new ones. Why? As growing up, you'd be exposed to grown-ups saying things like this, right? And before you are even the age of 10 or something, you would know that grown-ups have this way of speaking where it's not literally true, but somehow it creates an image in your mind, and then you understand what they mean. And if you will develop this understanding, so will any entity that has to do next word prediction, right? Because the prince had a heart of, if it does prediction muscle, it'll be wrong. So it'll learn too, right? And not only would it know what a metaphor is, it'll be able to create new ones. Because often there are new metaphors which you haven't seen before. before, you understand immediately, and so will this entity. So this is a simple procedure, right? How to express something as a metaphor, right? Create a new metaphor. And all complicated reasoning and even writing complex English is procedural. So here's an example. Give me an example of a piece of text with 2 sentences that could appear in a fiction about sushi and which exhibits use of metaphor and ad hominem attack. If you don't know what ad hominem attack is, you'll see in a second. Okay, so as Akira Sushi wrote on the plate, each piece was a delicate poem of the sea. So that's a metaphor. And it's created on the fly, right? Poem of the sea. Whispered with precision and care. Hideki was never mastered the art of what he had already called it, or price fish. So that's the ad hominem attack. And this was from 2023. GPT-4o. And here again you can say, okay, fine, it gave you some answer, but is it just copying from the training data? And the answer is no. Maybe it was in this case, but if you do many such trials and you see that GPT-4o can always do it, then you start realizing the number of combinations, depending on how many skills there are and how many skills have to be combined. And we'll do this calculation in the next talk. The number of combinations that GPT-4 can execute is larger than its training set. Okay, so that's a probabilistic argument, but it can be made precise. So this was the skill mix evaluation, and in 2023 we said, okay, this shows that the models are capable of originality. Any questions there, by the way? Or I move on? Yes?
How do you distinguish originality with noise in the probabilistic distribution? Like if I would simply noise my training distribution and then say, okay, this is now originality.
You would meaning the model would?
Yes. So
the model is going, whatever it is, it's probabilistic.
Yes,
yeah.
But what is originality and what is, for example, just our noise that happened without a different word here?
I'm not sure what you mean. So there's a list of skills. That's what this skill mix evaluation was. There's a list of skills, and you take random k tuples of skills and ask it to create text for those k tuples and see that it did a reasonable job. And the number of k tuples of n of a set of size n, and then choose k, which is n to k.
Or let me make the argument from the first sentence you showed. If you trained the model to precise.
No, just this. Let's restrict to this.
Okay.
This. We agree that it's. Yeah, just this. It's something plain version. Okay, so next word prediction requires mix and match of skills. So not just when we as evaluators are creating these very silly questions, sushi and all that. Just normal next word prediction requires mix and match of skills. So okay, so this sentence was clear enough, right? It's just you should just remember what you buy and convey. But how about this? Stepping into court and coffee with his 2 kids, raw light assigned by the register, binary day, 10% off if you want to buy. These things also happen, right, in real life. And now, in order to do next word prediction here, needs binary and needs to do some thinking, etc. Right? And models can do these kinds of things too. And indeed, that was a discovery in 2023 or 2022 that OpenAI was scaling up these models and discovering that they keep getting new capabilities. And so that's something we'll also return to in the next lecture. Okay, so now let's think at some intuitive level how this ability to understand text and did not see arise. And by the way, these were the memes from 2 years ago, 3 years ago. This is a show bot. It's some crazy multi-eyed creature which nobody understands. So the idea was that you train the model on this vast amount of text which no human can comprehend, right? It's like all the text that exists. And they thought of it as a show bot. And then once it was a chat bot, like ACDL2025, it's show bot with the, oh sorry, not phase, FACE. Alright, so how do you think about training stages? So there's pre-training, which is this next word prediction on a collection of text. And the way to think of it is not that it's memorizing that text. There's not enough parameters. And people have tried to quantify them, like the degree of memorization that's even possible with the current models. So it's not memorizing that, it's creating some inner web of knowledge and skills and some high-level representation. This model is still error-prone, like, even for simple math questions, it may have a 2% chance of success. And then there's post-training, instruction theory, model literature, etc., which is specialized and is more expensive data. Or more high quality data. And it refines its ability, the show off, right, which has this huge amount of stuff inside it, to become more than an expert predictor. It can reliably access its inner web and answer questions based on that inner knowledge. Okay, so the pre-training stages, it's a little bit more, or quite a bit more complicated than just take a bunch of internet text and train on expert prediction. So firstly, that internet text can be very dirty or problematic, and that has to be cleaned up. That's done by automated means. And then it's also partitioned into categories, like this. And then training has multiple phases. And each uses a different data mix from these categories. So the correct data mix, how much textbooks you use, how much whatever web pages you use, etc. All of that changes. And in case you're wondering why there are different phases, well, this was experimentally discovered that this is beneficial. And and the way they think about these phases and how to set up these phases is that they discover these positive or negative synergies between learning on different types of data. So for example, it's widely known that training on code helps text. Okay? So there goes your stochastic parrot stereotype, right? Like, why would a parrot, by memorizing some piece of code, do well on text, but actually train on code and do better on text. Okay, and also there's limited amount of high quality data, so you have to use it strategically as needed, where it makes the most impact. Like Wikipedia is, I think, 5 billion or 10 billion words. It's very tiny, but it's high quality. And finally, training uses synthetic data produced by another language model. And that makes no sense for, and actually it could even be data produced by the model itself. So that makes no sense. Like if you're thinking about it as a stochastic pattern, right? Training on your own text. Okay, now post-training. The first step is fine-tune on question and answer. So here's an example of a question answer pair that was used to train. So train means, the question is there and then you're training on an answer. So by next word prediction, you're training on the answer. And this is from a data set called body, and size 30,000. By the way, this body data set was created by Databricks by just telling their highly qualified workforce, just on your coffee break, just create a few questions and the answers. Okay. How many people think that's a good idea? I mean, so that's people like us, right? How many people think that's good enough? Nobody thinks it's good enough? You don't trust your So you think it's good enough? Right? Highly educated people, they come up with questions. So these are questions that educated people ask or think are interesting, and they write the answer. So what could go wrong? Right? Seems pretty good. We all are highly educated, right? PhD, whatever, maybe masters. Okay, so actually that answer is wrong. So this answer, that they found in the house, blah blah. I grew up in a town in India where camels used to roam around on the roads, and that's the answer I heard. But that answer turns out to be very incomplete. So if you ask GPT-4, it gives you this more detailed answer. And I checked it. You go to the appropriate sources and you see all this information. So why is this answer better than that? Any thoughts? Yes?
It encompasses more aspects, provides more complete.
No, it's definitely more detailed. But just for the purposes of training the model, why is the first answer bad? It's a subtle thing. I see your puzzle. So let me just explain what yeah.
I think that if you provide the model with only the shorter answer at the top, you're implicitly also limiting it to provide the rest of the answer.
Exactly. You're training the model to be lazy and unhelpful. So in its training, just as I was able to find this information on the internet, it did see this larger answer. Maybe not in one place, but certainly in many places. It knows that in its inner web of knowledge. And if in this phase you train it to ignore all that wealth of knowledge and give the lazy answer that even I knew as a 10-year-old back in India, you're training it to be lazy, and that's not good. So this stage requires really high quality data. Okay, and that's where human data is needed, and an industry colleague even phrases it as human data is the final mode. Now that there are open models and cheaper models, etc., human data. Okay, the other stage in post-training is reinforcement learning, where you improve the question answer capability using human feedback. So the model is made to generate many answers for a query, and humans rate them. And then you use the model's own answers for training. So that using calculus, you train on this objective where you slightly increase the probability for the preferred answer and decrease the probability for this preferred answer. Okay. But again, it's using the cross entropy loss calculation, but that's the semantics. Now another thing is that you can ask humans to rate it, but that gets tedious and expensive. You can just use 10,000 human answers and then train a model to provide this feedback, and that works pretty well. Okay, so you see here already it's much more complicated than this next word prediction. I mean, there's this feedback loop, and here there's a model actually giving feedback, etc. And the step 3 is just like what I said before, but now for safety. That's another important step, that safety, alignment, being polite, etc. Okay, so same kind of thing, but it has to learn what's appropriate and what's inappropriate, and that's done with a similar pipeline. So that's post-training.
I have a question.
Yes.
Do you make the assumption that the data is always
Which one? Pre-training or?
everything? I mean,
Go ahead.
a lot of false data.
Okay, so the question is, can data be bad, and what effect does it have? So it depends, yeah. So it seems that some amount of bad data is okay. The training is robust, right? If you 99% is right. So I don't know the exact percentage, and it also depends on the quality or bad quality of the mistakes. But so there's some robustness in this pipeline. But yeah, I mean, it's hard to quantify that, right? Like the quality, yeah. But yeah, it's something to worry about. Any other questions? Moving on to, like, we've done pre-training and post-training. So any questions on that? Yeah.
If it's for the data that you have inappropriate data, maybe how about the humans who rate it? If they prefer the lazy answer, then of course the model learns to become lazy, right?
Indeed, yes. So yeah. So the question was, like, if you're outsourcing it to people, right, and they are lazy, then you create bad data. Indeed. So you have to, just as you have to carefully prompt the model, you have to even more carefully prompt the raters and the creators of those questions. Like, what are you looking for? So you tell them, you can take 10 minutes and look up the information or whatever, and create a nice answer. Yeah, I've heard of like, for really crucial things, like companies are paying $1,000 per round per question. Okay. So next topic, metacognition. So again, moving past this stochastic parrots viewpoint. How am I doing on time? Oh, 32. Okay. So metacognition, and this is a question. Are they aware of how they're solving the task? Like network predictor, it's sort of robotic, right? It's runs some distribution and it's just churning out words. And are they aware? Now, of course, they're not aware in the sense that we are, because you can just turn off the model and start it up again, and it has no memory of what it is. So it's not aware in that sense. But at least does it have some internal process going on that tells it, okay, this is what I'm looking at, and this is how I'm going to solve it. So this was this paper that we did on metacognition. And let's start by thinking about what it means in this context that humans are aware. Okay, so when I give you a question like this, not a very difficult question, how do you go about solving it? You read the question, you try to understand, okay, what's the situation? And now you realize, okay, I have some kind of a geometric series, every minute the sinus sets what are equal to half the current amount, etc., etc. And then you realize, okay, I have to do the geometric series and whatever, right? So this is humans reasoning about their own part of things. That's metacognition. When you look at that question and start thinking about, okay, how do I go about solving it? That's metacognition. Or an example of metacognition. And this was, there's a seminal work by Flavel, and then these are some other things. And it's important for humans because when kids have learning difficulties, teachers are encouraged to use this metacognitive approach. Teach them how to solve. Or for example, kids who have difficulty in reading, they are taught using metacognitive skills. How do you read well? So, what about models? What is metacognition models? So here's an example. There are more examples, and there will be a lecture later on about it too. So give me an example of an obscure skill that may not even have an existing name. So GPT-4o, this is a few months ago, I think. I did it for this talk. So the GPT-4o told me linguistic exorcism. So I immediately go to Google, put this term in to see whether it exists, and Google didn't know about it. So I said, okay, that's a skill. So give me, skill activity. So give me skills associated with this. If necessary, make up names consisting of up to 4 words connected with underscore. So 4 English words, that's a lot of expressive capability, right? So it can express names of skills. So it gave me these kinds of things: constructive language transformation, contextual interpretation sensitivity, etc. Does anybody have a clue what these skills are? Okay. It's made up these names, right? So,
Poetry.
poetry, okay. Okay. You may appreciate poetry, isn't it? Yeah, so, okay, so the point here was that, it's coming up with these things. Let's see. So I said, okay, give me fine-grained skills under constructive language transformation and, with the same kind of notation and an example. So it says, synonym substitution technique. He's lazy and useless too. He prefers a relaxed approach and is still finding his strengths. Tone moderation adjustment. Stop making mistakes. Let's focus on how we can improve this. Okay, so it's seen from its data that humans have these things going on, right? And we completely recognize what this is. But it has no name. And there's like all these categories that it has figured out, and it needed to figure it out in order to do next word prediction or whatever its training is. And it can attach these labels to what it's doing. So this is another. So we have many other examples like this. Conclusion.
How does such a language recognize incompleteness of binary or some?
Oh, so now you're talking about math. No, so math is a different thing. We might return to that. Yeah.
Say, I agree with them. I say, all Greeks are liars.
Yeah.
Is that true or false?
That'll make it. It'll totally make it. Yeah, I mean, it's read books on logic and everything. It knows everything that you and I.
Incompleteness of this.
Yeah. I mean, does it understand at what level? We don't know, but like, of course, it's read all the logic books.
So those are the.
Oh yeah, of course. It knows everything, right? It's read everything. So that's actually a very interesting point. Like where does all this knowledge, like this high level knowledge come from? It's reading the text, right? So the logic books you and I studied in college. And as it's reading that, it's like forming some high level understanding. I think that's my view of it. It's like pulling together things, and that web is created, and on demand it's able to pull out pieces of the web. And probably you are still not probing it in the right way. It's probably over there. That's why what I mentioned, the $1,000 per questions that they are giving. They're training the model like with those very high quality human questions, $1,000 a question, to exactly probe it in the web models. Okay, so now I'll briefly survey current AI techniques. So this completely goes beyond this stochastic parrots stereotype. So the first is scaling laws. This maybe you can still think of as a stochastic paradigm, but scaling laws. And these drive the entire field. And the original scaling laws were for pre-training, but now they're scaling laws for all other aspects of training. Many of them are not published because these companies stopped publishing around 2022. Okay, so these are motivated by the questions like this. You do a big training run, and then it turns out to be good, right? So you want some predictability. And so that's where the scaling laws come in. And this is actually, this figure is from a popular talk, so the quality, I wasn't using cross-secting, just intuitive quality. And this is model size on log scale. So scaling law is just that you train a sequence of models, and you see that they are roughly fitting a straight line. And so now you say, okay, if I were to train a larger model using the same kind of recipe, it should fall on this straight line, and indeed that's what happens. Okay, so your very first run, if you perfected your recipe with these 4 or 5 smaller runs, the very first run is quite good. that's scaling laws. And so this training recipe, learning rate, data composition, etc., is all extrapolated from scaling laws. Okay, so this is done at all stages of the pipeline these days in the companies. That there's some scaling experiments before you do the final round. Next idea that seems really bizarre. Certainly, I don't know when I first saw it. It seemed really bizarre. Multimodal models. So that's, of course, we need them. But the way it's done is very bizarre. So you take a language model, and now you take a vision model, like some of these, models that were trained on just images, and those develop some very good representation of images, semantic representation. So you take the vision models, and now you take the representation from some high layer of that model, and those are semantic tokens of the content. And now you just take those tokens and add it to the LLM at some layer, and let it process them just like other tokens, like word tokens. And that works. And you can do the same kind of thing with other modalities as well. So these days, robots are all are multimodal as well, and they can take commands in English. And that gives them, that makes the behavior less brittle. Because if they can reason using language, when situations change. In the old days, robots, where their behavior was brittle, they put them in a new environment, they couldn't function. But now they can just reason and then adapt to the environment. Okay, that's still a drawer, it's not like the drawers we've seen before, but it figures out, okay, that's probably a norm, I should put it. Okay, so third thing, now this is, starts sounding more like science fiction, the first time you hear it. So models help improve future models. So we've already mentioned small models clean up data for training large models. Turns out you can use current models to rewrite text, human text, in order to train the next one. And this text rewritten by a model, so it's human data rewritten by a model, is often better for training. Okay, so that really goes beyond the stochastic parrots viewpoint, that somehow it's mimicking humans. You rewrite the human data with GB4, and then we train GB4.5.
Sorry.
Yeah.
So can you define rewrite a bit further in this context?
Rewrite. So okay, so I'll give you a simple example. You want to know like these math data sets, JSM8K. You rewrite it, the answer, so take the human answers, rewrite them using GPT-4 and train your little model with it. It'll be much better.
So you're asking for a more structured answer?
Yeah, just write it in a nice way, yeah. Let it use its judgment, yeah. Yes?
Isn't this the same concept like with Van machines, when a machine is able to self-reproduce or even rewrite itself?
It's not quite that, right? It's not the code of the machine, it's the data, yeah.
But at some point, if it can start rewriting text, it can rewrite human code, it can rewrite its own code.
Oh yeah, sure, of course, yeah. Oh yeah, I mean, future models are even already, I think they are writing code, and yes, that is the next stage. They write their own code, yeah.
So you mentioned that companies now, they stop publishing new things.
Yes, for 3 years.
So the language models, they don't have access to these results. New things, new knowledge.
That's right.
So we have what they call AI nationalism.
Correct.
They do from themselves, they are builders for themselves.
Actually, the Chinese are publishing a little bit, right? DeepSeek, yeah, much more detailed than any American paper.
So this will have some kind of consequences.
We have, yeah. So actually, yeah, this talk is completely not discussing, all these ethics and questions of politics and what's good for humanity.
Because new knowledge is not accessible.
Correct. Yeah, this is a very serious situation. And some companies have open models, but yeah, even there, like Llama, gives you some training details, but not enough to reconstruct. This is again, even besides that, like, who has the compute, who has the data, right? At some point I did a calculation, you know, like, people are saying, oh, all these companies are, pirating the books, right? Yeah, like, and you do the calculation, let's say you take 1 million books, right? High quality books. 1 million books. You do the calculation, it's like $5 billion, right? To just get rights, or $10 billion. They can easily get it. But we can't. And this one, yeah, we already said this, use current model to do specialized training data. Okay? Number 4, distillation. And this is the main reason why AI costs less, right? Compared to 2 years ago, like prices have fallen quite a bit. So you use the largest, most capable model to generate tons of data, I'm simplifying, and use it to train a new model. And there's only a small problem. So you may make the model 10, 20 times smaller, and the performance is still very, very good. Alright, so that shifts the scaling loss, and it shifts the economy of subsequent training. Okay, exactly all those kinds of rewriting. And now finally, and this is the most important idea in the last year or two, self-improvement loops. What we call reinforcement learning, but I think this is a better phrasing to make it clear what's going on. So it originated in game playing, like Go players and so on, and the recent reasoning models like O1 and DBC, etc. Now, self-improvement we think of in humans is like you read the book and then you improve yourself, for example, or you think a lot and then you improve. And how do models do it? So this is a self-improvement loop. You start with a large question bank with solutions. Math. Think of math, but there are other cases like coding, science, etc. So there are puzzles. So these are cases where the answer is very, more or less clearly verified. So, all right. So now you give the questions to the model. Okay? This is not training yet. It's just inference. Give it the question. Ask it to generate many solutions. Okay, V1. That's 8, 16 solutions. And now you use some automated way, like a small model, to see which answer is correct. Okay, because there's a verifiable answer, like the final equation or the final number or whatever, or final line. You can verify that. And the presumption is that if you got that right number, then it must have done everything right. So you take the best of those and use the best ones for training. So training just means that the question is just given and then you're doing next word prediction on the answer. This completely breaks this naive thinking of stochastic parrots. Right? This is answer that the model itself produced. What sense does it make to train on it, right, as a stochastic parrot? Right? It itself produced the answer. Okay, so that's not the way to think about it at all. What next word prediction does is it's reinforcing your good thought patterns. So it had wrong answers, right answers, and you're reinforcing the right ones. And so that tells it, like it changes its inner network so that it now gives more probability to good thought patterns. Okay, so that's the loop. You keep feeding it questions, it keeps making these answers, and the best ones are used for training. That's a certain loop. Yes?
So saying this completely break the being a stochastic parrot because it come up with the answers itself.
That's right.
We also have to look on the other side. It doesn't come up with the questions itself. So
Good.
it's a limited.
Good.
Yeah.
Let's just hold it for 30 seconds. 30 seconds. Okay. So similar ideas in reasoning models. Okay, so that you've seen. And also informal math theorem provers such as DeepMind, AlphaProof, Alpha Geometry, which got IMO Silver, and I saw that team a couple of weeks ago, and now they seem pretty confident they would get gold if they want better. They're like IMO is history. There's DeepSeek Prover, and Princeton, we have a team that's done the Gödel Prover, which is the best open source prover out there. And now, addressing your question, how does this alpha proof or alpha geometry work? It's not given the questions. No. It comes up with questions. Okay, and that's self-clear. So it has some map, right? It knows some map. And it's given a tough question, and it doesn't know how to solve it. So it says, okay, let me play, just as humans would, right? Let me come up with a simple conjecture, a simple subcase, and try to prove that. And then, as it does that, and it's staying in context, all of that work, it can now cogitate, so to speak, right? All these things it has already done, they are sitting in context, and then it can scaffold that to solve the big question. That's what it does when it wins the world. Both in training and in instance. Yes?
Follow up, but aren't we then in the sense where we didn't now have to verify that the equation generator is not a stochastic parrot? Because if that's a stochastic parrot, then it generates equations that the rate.
Well, if that's a stochastic parrot, then you and I. That's what we would do. Right? Yeah, if you want to call it a stochastic parrot, then you and I are stochastic.
No, because from what I understand from what you're saying, then we prove the burden of proof and then proving that we don't get.
No. Then I'm saying I'm putting the burden of proof on you that okay, prove that you and I are not stochastic parrots. Yeah. Okay. All right. That's it. So, and agentic AI, which is where you there's society of specialist agents which work collaboratively to delegate tasks to enhance efficiency. And am I out of time? Yeah. Sorry. Okay, let me just tell you one thing. Weak to strong generalization. So this is the OpenAI paper. So they had, two models, weak and strong. They know the training set, so they come up with a new task that's not in the training set. And weak AI spot this task as usual. And now n new questions are provided. The weak AI tries to answer them and share its answer for everyone. Now weak AI may get, 60% accuracy. Strong AI learns the task from these weak AI's answers and generates answers to the remaining questions. And its accuracy improves from 60% to 70%. This again breaks the stochastic parrot structure. It's learned from the weak AI, but weak AI made mistakes, and it says, oh wait, this doesn't make any sense, and it learns to do it better. It's kind of like the stories about cows or one of those geniuses. Okay, and this actually happens also in much smaller nets. This is a new paper that I have with some colleagues. It's just with two-layer nets, but even with two-layer nets, you have the weak to strong phenomenon. And we come to, where are we going here, right? So, in the previous picture, strong was, the human, right? But now suppose, or a bigger model, but suppose now strong is a model that's bigger than us, more strong. That's super AGI, and people are thinking about, how to keep it aligned. So to conclude, models are indeed beginning to understand. AI is weird and might be getting weirder. Thank you.
Any questions? The speakers will be around, so you can talk to them. That's the next thing.